Water made it possible for life to begin on the planet. It remains to this day our most important natural asset. Currently, in some parts of the world, natural resources fail to meet the full demand for water, making it necessary to turn to alternative sources. By using desalination technologies, it is possible to convert seawater into drinking water. In some areas of the world, it is even the only possible supply option. There are two types of desalination processes: thermal or membrane-based. The latter includes reverse osmosis, the most widespread and sustainable technology available today. Osmosis is a natural phenomenon that occurs when matter is exchanged between two solutions that have different concentrations and which are separated by a semi-permeable membrane. The concentrations of these two solutions become balanced spontaneously without the need for energy. This process can be reversed artificially by applying energy. If we apply a force to a volume of seawater containing a high salt content and pass it through a semi-permeable membrane, we obtain water with a very low salt concentration on one side and highly concentrated water called brine on the other. This process is called reverse osmosis and has been industrialized to the point where millions of liters of fresh water are obtained from seawater worldwide. The desalination process begins with a seawater intake, mainly through open intakes or beach wells. Open intakes allow for larger water flows to be collected and are therefore the most recommended method for large desalination plants. However, the quality of the water they provide varies over time. It can be affected by the presence of turbidity, changes in temperature, discharges into the sea, or the effects of storms. The well system provides a better and more stable quality of water, thanks to the natural filtration process that occurs in the ground. For the seawater intake, pumps are needed to drive it to the plant. These can be negative suction pumps located on the surface or submerged. With a submersible pump, seawater flows into it through the gaps in the pump impellers, where it is then propelled radially thanks to the centrifugal force. These impellers are connected to a single shaft, powered by an induction motor. By alternating impellers and diffusers, the pressure within the shaft is increased at each stage until sufficient pressure is reached to drive the seawater to the desalination plant. Seawater must be pre-treated to a greater or lesser extent, depending on the type of intake and the physico-chemical properties of the water. In this first pre-treatment stage, the most commonly used technology is filtration, using substrates of different granulometry. Most of the suspended solids larger than 20 microns are retained here. These filters become dirty and less effective over time, which is why they must be backwashed periodically. Although the technological development of reverse osmosis has made it possible to reduce the use of chemicals, the use of antiscalant prior to the process is still common to prevent the deposition of salts on the membranes when operating at high recovery rates. Cartridge filters are an additional safety system that is installed upstream of the pumps and reverse osmosis membranes. These filters ensure their protection by retaining microparticles that have passed the previous pre-treatment stages. Their filtration size is normally between 1 and 5 nominal microns. Once the water has been pre-treated, it needs to be pumped into the membrane rack with sufficient pressure, typically between 50 and 60 bar, for the reverse osmosis process to be carried out efficiently. A high-pressure pump is used to achieve this. This is the heart of the desalination process. The system consists of racks composed by a series of pressure vessels, each of which houses a number of membranes, usually 7 in series. The reverse osmosis process begins when pressure is applied to seawater, forcing water molecules tangentially through the membranes. Between 40 to 45% of the water passes through the membrane's surface and is directed towards the permeate or product collector. This water contains trace amounts of salts, as up to 99.98% of the salts have been rejected by the membranes. The other portion of water, approximately 60%, leaves the membrane rack at high pressure, still containing a large amount of salts. This water stream is called brine. The energy contained in the brine stream in the form of pressure is harnessed by energy recovery systems, which help to reduce the overall energy consumption of the desalination process. Many different systems exist. The most commonly used are those based on isobaric chambers. The potential energy in the form of pressure is transmitted from the brine to the same volume of seawater to be desalinated, with an efficiency of over 95%. The seawater leaving the energy recovery device does not have the same pressure as the seawater leaving directly through the high-pressure pump. Additional pumping by using a booster pump is needed to equalize the feed pressure of both inlet stream to the rack. After passing through the isobaric chambers and having transferred its pressure, the brine leaves the energy recovery device at low pressure and is discharged into the sea, using mechanisms that ensure its correct dilution and dispersion, so that its discharge does not affect the marine ecosystem. The desalination process culminates with a post-treatment. Desalinated water is corrosive. It must therefore be remineralized to achieve a balance in which the pH, alkalinity and calcium levels become homogeneous and stable during the water's further distribution. There are several remineralization techniques, the most widespread being CO2 injection, together with the use of calcite beds that add calcium carbonate to the water. With them, it is possible to adjust the pH of the water and increase its hardness and alkalinity. After remineralization, if the water is intended for human consumption, chlorination is carried out in the distribution tanks in order to comply with existing health legislation. Under this legislation, the water put into the network for human consumption is subject to strict analytical controls to ensure that the required technical and sanitary criteria are met. Finally, water is distributed to the city, agriculture and industries through hydraulic networks and pumping systems.